In this video, I'm going to walk through the creation of a hash table in C. And to resolve conflicts, I will use a linked list at in each element of the hash table. Okay. So since I said I'm gonna kind of do it in reverse. First, I'm gonna start off by creating a linked list structure, and then we'll go ahead and create the actual hash table. I'll try to explain as I'm going along. So I'm going to be using the heap, and I'm going to need stdio because I need to, I'm going to have to print some stuff. And then of course, if we're using the heap, I'm going to need stdlib. And main, let's just get a main set up, make sure I can get it compiling easily. Desktop. Maybe I'll just call it hash table.c. Alright. And let's go to the desktop. Where am I? Hash table.c. Just get it in a one-liner. Alright, looks good. So to start off, I'm going to create a linked list structure. Just like creating any linked list in C, it's not going to differ. And for this video, I'm just going to do insertion. I won't do deletion, just because it's not really the point of the video. The point of the video is really the hash table itself. So we're going to need a structure for the actual node. And let's just make it hold a value that's an integer. And of course, for the linked list, you need to be able to point to the next node. And for the type def, just node. Simplify the syntax a little bit. Okay. So, like I said, only insertion is going to be supported in this video. So let's name the function for insertion, insert new node. And I'm going to make it I'm going to make this function take in the head of the node, and then I don't want it to actually return it. It'll just make it simpler, because then at the end of this function, when it's done, I want to be able to do something like node head equals null, and then just calling insert new node with whatever I get in here, and not actually assign it back to head. It'll do that in here. Okay, so insert new node. We want to pass in the head, like I said, and the new value. So int new value. All right. So just like you may be used to if you've done this, if you're not new to C, if you are, that's okay. So first I'll create the actual new node. I'm going to have to do this whether the head exists already or not anyways. And like I said, I'm going to use a heap. Malloc. Size of node. And we're going to add it. We're going to add the value. New node equal, whoops. The value of new node should be set to the new value we're passing in. And we're going to always add it to the tail of the list. So new node, that's always going to have its next pointer as null, because we're adding it to the tail. Okay, so first we're going to see is our head already null? Well, if it is, then we'd better create the head. And since we already have the new node up here, all we have to do is assign head to it. And that's it. Since we're using double pointers, we're not going to be getting the stack address back, and the head will be set outside of the function for us. And if head was already set beforehand, then we're going to have to do a traversal. Let's name another node current, and we'll set it to head. This is what's going to go through the whole list. So we're going to find the tail of the list. While current next is not null, so while we don't hit the tail, go get closer to the tail. Okay. And then once we finally break out of this, the next place is going to be current.next is where we actually want to add new node, because it'll serve as a new tail. And that is it. We don't need to do anything with head because head's not going to be changed. That's it for this. So let's test it with a few values first. Insert new node. Head 5. Insert new node. Head 6. All right. And let's print these out. Print of. We'll do a new line in between them. Double pointer. Well, this is just going to be head dot value. This should give me 5. Oh, I'm gonna mess something up. Something simple. Ah, of course. Whoopsie. I just need to pass the address. Okay. 5. And if we go to the next, it should point to 6. Next. All right, 6. And if we go even next, this should give us a segmentation fault since it's going to be null. Yeah, this isn't the best way to test it, but it's a pretty simple algorithm for it. Yeah, segmentation fault, good. We know we hit the tail. All right, so that's the entire linked list portion of this video. So let's actually move on and get to the hash table itself. Now, I'm going to make the table of a size 11. It's a good idea to keep it prime. It spreads out the, it makes it more evenly distributed, the values that you push in there. But then again, that does depend on the hash value. And the hash value I'm going to actually have is going to be probably the simplest hash value you could possibly have in this. It's just going to be a straight modulus, but I'll get to that after. Just for testing, don't actually use that. It's not a good hash value to use, but just for the purposes of this video, I'll use that. Okay, so first we gotta actually create the hash table itself. I'll have that done inside of a function. Get hash table. I'm going to erase this stuff here because we won't need it. Okay, get hash table. So we're going to do it on the heap. Node hash table equals. Now, this is an array. It's going to be an array where each part of the array has a pointer to a node, and that node will be the head of the list at that array index. So we're going to make use of the size and calloc, and each one is going to be the size of a node pointer, and then I'm going to return. That's it. The actual individual heads, I'm not going to create them yet. There's no point. It's just we're just going to be using up space beforehand needlessly. We might not even be using all of them. Okay, so that'll grab our hash table, and you know what? I'll just go ahead and write the hash value. This is, well, you know what? No, I won't do that. Well, we'll go a little bit slower. So we need a way to insert something into this hash table, which is going to be the actual bulk of the function, but it's also not too long. So I'll just name it insert into table, and we need the table itself being passed in, and the new value. Oops. Okay. First step, we need to actually find where in this hash table do we want the value to go. So we have to generate a hash value. I'll just name that location. And we're going to need, I'll make another function. I'll just call it getLocation. And all it does is it takes in this integer value, and it's going to spit out a different integer, which is going to be a location. Since we know the hash table size is 11, it has to be between 0 and 10, which we can make use of a modulus function to do. So get location new value. I'm going to use the simplest possible hash value, and I'm just going to make a note here. This is terrible to use in real world applications. Okay, just so you know that I know that. Okay. The hash value I'm just going to use is, you take the new value and you just take the modulus by the hash table size. So it'll always be between 0 and 10, the simplest hash value in existence. Okay. So we got our location. Now we can, since we have the location, we can take a look inside that location and see if was the head already created there. So has this been accessed before, essentially. So at that location, is it null? If it is, then you actually have to create the head. This is where we're going to allocate the space required for the head, which I did not do in here, because that would have been a waste to do it there. Okay, malloc, size of node pointer. Okay, that's where our head's gonna go. And speaking of the head, let's make the variable for it. Node head. We'll just name it null for now, because it's going to be passed in here. It's going to check for the null inside insert new node. And so we can call it head, and you pass in the value. Oh, you need a pointer to a pointer because it's a double one, or the address of this pointer because it's a double pointer being passed in. New value. Okay, that'll insert the node for us, which we already checked. It works. Then we have to just set the hash table location. Just make it point to the head. Okay, now that's it for this part of it. If the head was already there, on the other hand, then your head is going to point to it. It's going to point to, we're going to name the variable to point to the head. Okay. And then you insert a node there. Insert new node into head. I keep doing that. Head, new value. And the location, you set the head again. And that's it. Actually, you know what? I got some duplicate code in here. If this and that. This is the only part that's different. Yeah, these two can. You know what, I'll leave them in there because then I'm going to have to move head outside. This is clear anyways. And this will insert the value for us into the table. Now, how do we know if this is actually working? We need some way to display all this. So let's go ahead and write a short function just to display the actual entire hash table. I'll put it here. Void display table. And we pass it the table. Okie dokie. We're going to traverse through. We're gonna look at each of the heads essentially. Is the head even there? If it is, then you go through the linked list and we'll print out the numbers. We'll print everything on a uniline. I'll try to make it look a little bit pretty as well, just so it's easy to see. So we have to traverse through each of the indices. And we're going to have to check each of the heads. So hash table I. And you know what? I'm going to actually add a print statement here just to print the index, which is an integer. I'll put a colon there too. Okay, so if the head is null, I'm going to actually print, I'll print null. Let's do capital letters since it is C after all. Okay. If it's not, this is once again a linked list traversal like we did previously. Okay, so as before, node current equals head while current is not null. If current isn't null, we know there's going to be a value there. So we're going to go ahead and print that value. Printf. Since it's an integer, I'll print a space after it as well. And the value at current and we're going to go ahead and move current forwards. Current equals current dot next. And should I forget something? No, this looks fine. No, I need a new line character, just so I can print everything on its own line. That should be it. So, how do we go about testing this? Well, first, we got to grab the actual hash table. So node, hash, I'll just name it table. Table equals get hash table. This will grab the hash table for us. And then we can insert a whole bunch of stuff. Insert into table. Table. We can insert some values. So 0. That'll put it to the first spot. Let me just copy this. Let's triple this up. Okay. Let's change around some values. So 2, 78, 12, 9, 6. Again, 10, but 11. And actually, I just realized somebody watching this video is going to point this out. What if it's a negative number? Well, if it's a negative number, then let me put it in here. I forget what the actual function is for it, so I'll just fix it myself. If new value is less than 0. Ooh, I got an error here. Forgot the int. New value is less than 0, then we'll just make it positive. Alright. So just multiply it by -1. So there, I got it before you. Whoever was going to point this out. There, I'll put one there for you too. Okay. Okay, that's good enough. And then print. If I got all this right, it should work fine. Should. Okay. Alright, let's see how it goes. And there you have it. There is our hash table. So, some good things and some bad things about using a hash table like this. I'm not talking about the hash value or the size of the table. I just mean using a linked list to resolve conflicts. The good thing is that you can always add something as long as you have, well, as long as you have memory, I should say. But you can always add stuff, and you don't need to worry about resizing. However, the bad thing is that if you have a whole bunch of values and the size of your hash table isn't that big, you're gonna have to do linear traversals. So, like if I wanted to find 1, then I'd have to not only use the get location method on it to find which index it's in, but then I'd have to actually go to it. And of course, for of course, there is one way around all this, and that is to increase the size of your hash table as you need it dynamically. So, like for example, let's say if your hash table filled up halfway, you might have a trigger to actually double its size, but then that comes with its own issue in that you're going to have to spend time remapping everything based on the new modulus value. But anyways, I hope this was enough to get anyone started. If you're learning C or any other language and you're just kind of wondering about hash tables, the general idea is just to get a value out of some input so that you can map it to an index in a list structure. And the way of resolving conflicts can vary depending on what you need the code for, but this is one way to go about it. So that's it for this video.